Morning, everyone. My name is William. It's a bit hard to pronounce my full name. I'm a PhD student at Center for Quantum Technologies at National University of Singapore. And today I will explain to you a recent numerical method that we use to characterize the behavior of any classical quantum broadcast network. And this is a joint work with our postdoc Yukun, Emilian, who is sitting over there, Antonius, and my supervisor Charles. So today's talk will be divided into two parts. Firstly, I will explain how our numerical method works. And in the second part of the talk, I will use this numerical method to analyze the security of quantum key distribution. And the protocols that we are going to present today are the phase encoding BB84 protocol, and also three-state protocol with time-bit encoding. So before we start, let's recap like a few examples of broadcasting that we encounter daily. A classic example would be like television broadcasting. This year we have the World Cup in Russia, but luckily because of broadcasting, people all over the world can watch the matches. Another application of broadcasting would be in group chat. We have this messaging application, WhatsApp or WeChat in China. And using this feature, we can send messages to multiple users of the applications. So more abstractly, what happens is in a broadcast network, we have where's the laser? We have a classical. We have a sender which send message Z and encode it and then transmit it in this one. So there is encoding the message Z and send it through the broadcast channel, and we have the receivers Alice and Bob, which will to obtain the information A and B, they will need to use some decoding function X and Y, and this decoding function can correspond to like the choice of television channel that you want to watch in the case of the television broadcasting. And the behavior of this broadcast network is described by the probability of Alice and Bob obtaining outcome A and B, given that they use input X and Y and the sender is sending message Z. So what happened when we use a quantum channel instead is that first, the encoding will be in terms of some non-orthogonal quantum states. And when we send it through the quantum channel, in general, this state might evolve. So to describe the evolution, it's convenient to work in the purification picture where the evolution is described by some unitary operators. And one feature of the unitary operators that the overlap of the input states would be the same as the overlap of the output states, i.e. the unitary operations will preserve the inner products. So to obtain information A and B, Alice and Bob will perform some measurements on the output states, which is now shared between them. And in general, this measurement is described by POVM, but since we work in purification picture where the dimension is not bounded, we can, without loss of generality, we can consider projective measurements. And we also assume that the measurements that Alice and Bob are doing are actually separable. That means the commutator between the measurement of Alice and Bob is 0. So given this model of like a quantum broadcast network, we want to ask the following question. So what are the behavior that are allowed by quantum physics? So let's recall like some features of quantum information. Firstly, non-orthogonal quantum states cannot be cloned perfectly. Another feature is that when we measure the quantum state, in general, we perform we give some disturbance to the quantum state. And since we use non-orthogonal quantum states, in general, there is no measurement that distinguishes them perfectly. So all these features actually give some fundamental constraints on the correlation behavior. So to be more explicit, actually, we can write down two constraints on the allowed behavior. Firstly, given by the Bond rule, where the probabilities must be expressed in terms of some states and measurements. And another constraint comes from the choice of encoding that we do. Because of unitarity, the inner product must be preserved in the output state as well. So one nice way to answer this question is actually to consider all the states and measurements that satisfy these two constraints. But unfortunately, this problem is very difficult, or if not impossible, especially if the dimension is not bounded. Luckily, we don't give up here, and we can still consider an alternative method that is using semi-definite relaxations. And this has been proposed before in the context of quantum non-locality by Navasquez, Pironio, and Asin. And that's why this method is now famously called the NPA method. So this is actually a solution to the special case of our problem where the source is fixed. That means only one value of z is allowed. So for the benefit of those who are not very familiar with the NPA method, we'll go through very quickly how this method works. So now we have the set Q, the quantum set, which is the set of behaviors allowed by quantum physics. So now we can consider a bigger set Q1, which is the set of behaviors that is consistent with the existence of some positive semi-definite matrix, which is also associated with set of operators S1, which is the set of measurements of Ellis and Bob. Now we can see that the set Q is actually smaller because, like, for a given states and measurements, we can always construct the PSD matrix G, but not vice versa. That's why the set Q1 is bigger. And the idea behind NPA is by considering bigger and bigger PSD matrix, we can always obtain a tighter approximation of this quantum set Q. So now we have the set Q2, which is associated with another set S2, which is basically just S1 plus some other operators, which are sequences of two operators. So using this hierarchy of semi-definite relaxations, we can actually obtain a tight approximation of the quantum set, and NPA actually proved that if you do this sufficiently many, you will converge to the quantum set Q. So our contribution here is to generalize this method to include multiple states, and we use the inner product constraint on the states. So it turns out that the inner product constraints translate to a linear constraints on the matrix G, which is here. So its block here now resembles the NPA moment matrix, where the diagonal blocks define the constraints on the probabilities, whereas the off-diagonal blocks define the constraints on the inner product. And we also show in the paper that this hierarchy also converts to the quantum set. Now we come to the second part, where we are going to use this method to analyze the security of QKD. So first we consider the protocol proposed by Hagner et al., the phase encoding BB84 protocol. So in context of QKD, now Alice is playing the role of the sender, whereas Eve is playing the role of the second receiver. So in this protocol, Alice is going to prepare the state plus minus alpha, which are coherent states without phase randomization. So the plus minus alpha states are used to generate the key between Alice and Bob, whereas the state plus minus I alpha is used to estimate the information that Eve has. Now Eve is free to perform any unitary operation on the states, and at the end of the channel, Bob is going to perform some measurements, which in the protocol it corresponds to some interferometer, but we treat this measurement as black boxes now, which takes input 0 or 1. This corresponds to the measurement choice of Bob, whereas it outputs the bit 0, 1, or sometimes inconclusive outcomes. This corresponds to the case where Bob's detector does not click. And an important assumption that we are going to make here is that this inconclusive outcome does not depend on the choice of basis that Bob is going to make. And then to use our method to get the secret key rate for this protocol, we first apply the unitary operations. Now we don't care about the output state phi as long as the inner product is preserved. Then after that, we assume collective attacks and asymptotic case, and therefore we can use the Diffie-Winter bound and the entropy uncertainty relation to arrive at this formula. The generalization to security against general attack can be done using theorems like definity theorems or entropy accumulation theorem. And then this B error rate is observed in the experiment, but this one is not. So we need to perform some optimization there, and that's where our method comes in. So we maximize the phase error rate, constrained on the observed probabilities such as the detection probabilities, as well as the B error rate, the QBER. Then we use the second level of the hierarchy of our method to obtain the following secret key rate. And as you can see, that this is actually better than the one obtained using the low Prescale method proposed in 2007. So here we have some recent results that actually use the low Prescale bound, and that means now using our method, these results can get a free upgrade on the secret key rate for free. And to show that our method can work for non-standard QKD protocol, we consider the following protocol, which is actually inspired by the coherent one-way protocols. But there are some differences, so we don't claim that we have proved unconditional security for cow. So firstly, in this protocol, we don't measure the coherence between like parsers that are separated by the vertical lines like this. So we don't measure the coherence between these two parsers and these two parsers. Secondly, in this protocol, unlike in the original cow, we consider active measurement choice. So we have these switches that will determine whether Bob is going to measure in the data line or the monitoring line. And last but not least, in the cow protocol, the test state is fixed to have the same intensity as the signal states. But in this protocol, we are free to optimize the intensity of the test states such that it gives us the best key rate. So again, playing the same game and using, again, the second level of the hierarchy, we obtain the following key rates. And as you can see, that by optimizing the intensity of the test states, you can get a much, very significant improvement compared to the case where the test state intensity is fixed to the signal state intensity, which corresponds to the cow states. And so we come to almost the end of the talk. To summarize, we have proposed a numerical method based on SDP that is also efficient to characterize the behavior of any classical quantum broadcast channel. Important features about our method is that this method is independent of the dimension of the system. So it also works for protocols with coherent state encodings. And another important features is that it requires minimal assumption on the measurement devices. And because of these two features, our method is powerful due to the being versatility, and it's applicable to any discrete prepare and measure protocol. And I want to emphasize that this method also works beyond QKD. Then in the second part of the talk, we apply this method to analyze security of QKD, and we can get higher secret key rate compared to previous results, as well as our method is very versatile and can be used for non-standard QKD protocols. So some ongoing works and open problems, I want to emphasize that this is not exhaustive due to the versatility of our method. So we want to analyze the security of distributed phase reference protocols, as well as those hybrid discrete variable and continuous variable protocols where you perform some discrete modulation, but performing homodyne detection. Then we want to consider different constraints, such as the energy constraint or the constraint on the fidelity, other than the inner product constraints. And last but not least, we will also want to extend this method to the MDI QKD scenario. And actually, for the last one, we have already done that. And here are some preliminary results. And as you can see, that this also leads to improvement compared to previous results by Tamaki et al. For the phase encoding MDI QKD. So that's all from me. Thank you for your attention.
Thank you. Any questions?
On your results slide with the optimized beta amplitude, do you have an order of magnitude how large they are and whether they change as a function of the loss?
Yes. So for each point, we optimize both alpha and beta, and for the high loss scenario, the value of optimal beta is roughly 1/4 of alpha. So in terms of the intensity, it's half.
Thank you.
I have a question about the coherent state protocol.
Yes.
Our numeric method as well gave some improvement. Do you know basically how your improvement compares to our improvement?
So compared to the numerical method that you proposed?
Exactly, yeah. Because it would be interesting to know whether it's exactly the same or is it different, because there are different approaches, right?
Yes.
So
yes.
It's not clear that they would be the same. So therefore it's interesting to know how they compare relatively to each other.
Indeed. However, we have not really compared the two.
Okay, so we have something to do.
Yes, indeed. Okay.
Yeah.
What's the difference between your method and the MPA protocol? Did you feel more interest in the SDP matrix?
You can think of our method as generalization of the NPA method, where you have multiple states, and then we add the constraints on the overlap of the states. In terms of the like moments, they are pretty much the same. So each blocks of our matrix resembles the NPA moment matrix. Okay, thanks.
Maybe one more question.
Yeah, thank you very much for this presentation. Of course, I'm very pleased with the results. Can you tell, would you also guess, or am I correct, guessing that if one would also measure the coherence between pulses from different time bins, from different qubits, one would improve this result?
We believe that is the case because it can only improve, it can only help Bob to do that. The problem with that is that it will complicate the security proof due to some problem with application of the definity theorems or the entropy of conversion.
Okay, something more to do.
Yes.
Interesting. Thank you.
All right, thank you. Let's thank the speaker and all the speakers in this session. Thank you.